On a Tuesday morning in February 2013, the people of Chelyabinsk, Russia, woke to an ordinary winter day. Cold, gray, routine. Then, at 9:20 a.m. local time, the sky exploded. A streak of light brighter than the sun tore across the atmosphere. For a few seconds, the world turned white. Then came the shockwave. Windows shattered across 6 cities. Buildings cracked. Car alarms screamed in unison. Over 1,500 people were injured, most by flying glass. They'd seen the flash, walked to their windows to look, and the blast wave traveling at the speed of sound arrived moments later, turning every pane into shrapnel. The object that caused this chaos was an asteroid, just 20 meters wide, about the size of a house. It entered Earth's atmosphere at over 40,000 miles per hour and detonated with the force of 500 kilotons of TNT, 30 times more powerful than the Hiroshima bomb. And here's the thing that should terrify you. Nobody saw it coming. Not NASA, not the European Space Agency. Not a single telescope on Earth detected this asteroid before it hit us. It approached from the direction of the sun, invisible in the glare, a cosmic blind spot we still haven't fully solved. Chelyabinsk wasn't an asteroid impact in the traditional sense. The rock exploded in the air, about 30 kilometers up. If it had been slightly larger, slightly denser, or entered at a different angle, it could have reached the ground intact. The explosion would have leveled the entire city, hundreds of thousands dead. And Chelyabinsk wasn't even rare. Events like this happen roughly once every 60 years on average. The last one, the Tunguska event in 1908, flattened 2,000 square kilometers of Siberian forest, an area larger than London. If Tunguska had hit 6 hours earlier, due to Earth's rotation, it would have struck St. Petersburg instead of empty wilderness. We got lucky. Twice. But luck isn't a strategy, and the universe doesn't care about our schedules. Right now, somewhere in the darkness between Mars and Jupiter, there are rocks, millions of them, tumbling through space in a vast belt of debris left over from the formation of the solar system 4.6 billion years ago. Most of them stay there, locked in stable orbits, harmlessly circling the sun. But some don't. Gravitational interactions with Jupiter, collisions with other asteroids, even the subtle push of sunlight itself can nudge these rocks onto new paths. And some of those paths cross ours. These are called near-Earth objects, or NEOS, asteroids and comets whose orbits bring them within 30 million miles of Earth's orbit. As of right now, we've identified over 30,000 of them. That sounds like a lot until you realize it's probably only a fraction of what's actually out there. The smaller they are, the harder they are to see. And even small ones can cause catastrophic damage. An asteroid 140 meters across, roughly the size of a football field, could destroy an entire city. Regional devastation, millions dead. An impact like that happens statistically about once every 10,000 years, 10 kilometers wide, and you're looking at global consequences, mass extinction, the end of civilization as we know it. That's what killed the dinosaurs 66 million years ago. It hit what is now Mexico's Yucatan Peninsula, traveling at tens of kilometers per second. The impact vaporized the asteroid, the bedrock beneath it, and everything for hundreds of miles in every direction. Mega tsunamis hundreds of meters tall raced across shallow seas. Debris was thrown so high, it left the atmosphere before falling back, heating up on re-entry like millions of shooting stars. igniting wildfires across entire continents. The blast threw so much dust into the atmosphere that sunlight was blocked for years, maybe a decade. Photosynthesis stopped. Temperatures plummeted. 70% of all species on Earth went extinct. The good news is that asteroids that size are rare, and we've found most of them. Current estimates suggest there are fewer than 1,000 near-Earth asteroids larger than 1 kilometer, and we've cataloged about 95% of them. None are on a collision course with Earth for at least the next century. The bad news is that the ones we haven't found yet are still plenty dangerous. And there's another threat we've barely begun to address: comets. Asteroids get all the attention, but comets might be the real nightmare. Here's why. Asteroids orbit the sun in relatively predictable paths, most of them clustered in the belt between Mars and Jupiter. We can see them coming years, sometimes decades in advance. But comets live in the outer solar system. Some come from the Kuiper belt beyond Neptune, others from the Oort cloud, a vast sphere of icy debris stretching halfway to the nearest star. These objects spend most of their time in deep freeze, invisible, dormant. Then something disturbs them: a passing star, a gravitational nudge, a collision, and they begin to fall inward, toward the sun, toward us. By the time we detect them, they're already screaming through the inner solar system at speeds that make asteroids look slow. A typical asteroid impact happens at around 20 kilometers per second, fast enough to vaporize anything in its path. But comets can hit at twice that speed, sometimes faster, and because impact energy scales with the square of velocity, a comet carries roughly 4 times the kinetic energy of an asteroid the same size. They're also bigger on average. The typical comet is at least 3 times the diameter of the average asteroid, which means 3 cubed, 27 times the mass. Do the math. A comet impact could deliver over 100 times the destructive energy of a typical asteroid strike. Statistically, comet impacts are about 100 times less likely than asteroid impacts. But when one does hit, the damage is apocalyptic, which means, from a risk perspective, comets represent about half of the total threat to human civilization, and we've largely ignored them. In 2013, a comet called Siding Spring was discovered. Less than 22 months later, it passed within 135,000 kilometers of Mars. If that had been Earth, if the trajectory had been just slightly different, we would have had less than 2 years warning. Not enough time to mount a defense. Not enough time to evacuate. Barely enough time to say goodbye. The time required to design, build, test, and launch a reliable spacecraft capable of deflecting an asteroid is roughly 5 years. If a comet appeared tomorrow on a collision course with Earth, arriving in 2 years, there would be nothing we could do. Absolutely nothing. We'd watch it approach, calculate the impact site, and hope it hits somewhere that minimized casualties. That's it. That's the plan. But here's where it gets complicated. Not all asteroids are the same. Some are solid rock or metal. Others are rubble piles, loose boulders held together by weak gravity. When NASA's Double Asteroid Redirection Test Mission slammed into Dimorphos on September 26, 2022, it was testing whether we could predict the result. DART hit at 14,000 miles per hour. The impact was designed to shorten Dimorphos' orbit by at least 73 seconds. The actual result? 32 minutes, more than 25 times expected. Why? Dimorphos was a rubble pile. The impact blasted tons of debris into space. Boulders over 3 meters across ejected at 50 meters per second. The debris provided 3.5 times more momentum than the spacecraft itself. Mission success. But also surprise, the boulders weren't scattered randomly. They clustered in 2 groups, heading in specific directions. As one scientist said, something unknown is at work here. The physics was more complicated than predicted, which means if we deflect an actual threat, we better understand the target. Hit it wrong and you could fragment the asteroid, turning one impact into dozens, or nudge it into a gravitational keyhole, setting up a future collision instead of preventing one. Speaking of gravitational keyholes, let's talk about Apophis. In 2004, astronomers discovered an asteroid with a 2.7% chance of hitting Earth on April 13, 2029. A Friday the 13th. The asteroid was 340 meters wide, big enough to cause regional devastation. They named it Apophis, after the Egyptian god of chaos. Better observations ruled out the 2029 impact. But there was still a problem. Apophis would pass within 32,000 kilometers of Earth, closer than our satellites, and Earth's gravity would warp its orbit. If it passed through a keyhole less than a kilometer wide, the gravitational tug could set up a collision 7 years later. April 13, 2036. By 2006, that risk was ruled out. In 2021, radar confirmed Apophis poses no threat for at least 100 years. But the 2029 flyby will be spectacular. Over 2 billion people will see it with the naked eye, looking like a bright star moving across the sky. Earth's gravity will stretch and squeeze it, possibly triggering quakes on its surface. NASA and ESA are sending spacecraft to study it, nature conducting the experiment for us. But Apophis reminds us, if it were on a collision course, we'd have 5 years to act. Barely enough time. If we didn't know until 2027, 2 years, not enough. So how do we find these things before they find us? Telescopes. Surveys like Catalina Sky Survey and Pan-STARRS scan the sky every night, looking for faint dots that move against the stars. When they find something new, they track it, calculating its orbit. If it comes close to Earth, it gets added to the list. We're finding about 3,000 near-Earth asteroids per year. But small asteroids are hard to see until they're close, maybe too close, and anything from the sun's direction is invisible. That's how Chelyabinsk blindsided us. NASA is developing space-based telescopes to cover these blind spots, but funding is slow, and every year without them is another year we're flying blind. Then there's what to do once we find a threat. DART proved kinetic impactors work. Build a spacecraft, slam it into the asteroid, nudge it onto a new path. A tiny change years in advance means it misses Earth entirely. But this only works with time and the right target. For other cases, we have proposals. Gravity tractors that hover near asteroids and tug them off course. Nuclear explosions to vaporize surface material and create thrust. Even painting asteroids to alter how sunlight pushes them. Real proposals backed by real physics, but none tested at the scale we'd need. We've made progress. DART was a success. We're finding more asteroids every year. We're better prepared than ever. But we're not ready for a short warning comet or an asteroid we don't see until it's too late. Stephen Hawking called asteroid impacts the biggest threat to intelligent life, not climate change, not nuclear war. Asteroids, because an asteroid doesn't care about politics, it's just physics. A rock moving through space, indifferent to whether it hits ocean, city, or desert, and it's going to happen, not if, when. The B612 Foundation puts it bluntly. It's 100% certain we'll be hit by a devastating asteroid. We're just not certain when. The dinosaurs had no space program, no telescopes, no warning, no chance. We do. We have the technology and knowledge to defend our planet. What we don't have is unlimited time. Every delayed detection system, every budget cut, every postponed test is a year we remain vulnerable. On April 13, 2029, 2 billion people will see Apophis streaking across the sky. Some will feel wonder, some fear, and some will think about what might have been. Apophis will pass safely, this time. But out there are other rocks. Some we know, some we don't. And somewhere among them is the one with our name on it. When that day comes, we'll need more than luck. We'll need preparation, vigilance, technology, cooperation, and humility to remember we're not masters of this solar system. We're one species on one fragile world in a cosmic shooting gallery that's been running for billions of years. The universe doesn't care if we're ready. But maybe we can be ready anyway. Not because we're guaranteed to win, but because trying to survive is what we do. This time, unlike the dinosaurs, we get to see it coming. The question is whether we'll do something about it. So the next time you look up at the night sky, remember what's up. There isn't just stars and planets and cosmic wonder. It's also rocks, billions of them. Most harmless, some not. And between us and them is nothing but mathematics, physics, and the hope that we're paying attention. Because the universe has been throwing rocks at Earth for 4.6 billion years. It's not going to stop now. The only question is whether this time, finally, we're ready to catch one. Thank you for watching this video. If you enjoyed it, please like, share, and comment down below, as it helps let others know they should watch this video. Also, consider subscribing and hitting the bell to get notified of our newest videos. See you next time.